They didn't give you all any access to Google Drive links for the past papers yet, right?
No, not yet.
Okay.
Only we have the practice questions, which is included in LMS.
That's all. Okay. Let me get a update on that. Chalo, let us start. Hi, Anushka. Good morning.
Good morning, sir.
Different tabs. All right. So previous lecture, last lecture, which was last week, we had started with, we had completed research, we had started with Brownian motion. Yeah, we started with Brownian motion. This is the chapter that I say, or I recommend everyone to sit till lateral model, because everything that I do starting now is going to be through lateral model. Lateral model is entirely based on the fundamentals of Brownian motion and
Sure.
Your voice is not clear. It's some internet connectivity issue.
Sure. All right. Can you hear me from?
Yes.
Yeah,
Uh,
yeah, looks good.
So what I was saying is, previous lecture we had started with. Well, can you hear me proper now, right?
Yes, sir.
Yeah, this is
So
fine.
last lecture we had started with Brownian motion, which was Unit 2, Chapter 1. Till now we are done with Introduction to Principles of Derivative Pricing, Binomial Model, and Greeks. Now this is the chapter onwards that I recommend students to not miss out on any lectures. Reason being that Brownian motion till Black-Scholes, everything is going to be very much dependent on each other. The entire fundamentals, the entire concept of Black-Scholes is actually based on what we'll derive from Brownian motion and Ito's lemma. Need not Brownian motion ideally will get over today. Ito's process will ideally take like 3 lectures, and then we'll start Black-Scholes. So it's not a very long journey as well. It's going to be relatively short. So this is where I recommend students, because after that it's ideally just 2 small chapters that are left in the syllabus. Once we complete Black-Scholes, the next 2 chapters are ideally 1 1 2 2 lectures chapters each. Now the major crux of the chapter or the subject is still this particular point of Black-Scholes. Now, what is Brownian motion? What did we understand in Brownian motion? Uh, so till now, the option pricing model that we've seen is a binomial, is a discrete model, which is nothing but your binomial model. But I know practically my underlying asset prices are not a discrete process. They actually change continuously, and I need to monitor my derivative portfolio on a continuous basis. Hence, I now transition from a discrete process to a continuous process. In order to do that, the question statement arises that my underlying asset price will have to be given a continuous process, will have to have such a framework, will have to have such a model which is actually in a continuous time space, which can be predicted on a continuous basis. Hence, there came into the scenario, or there came into the question of Brownian motion, wherein based on certain empirical study, they said that Brownian motion is actually a good fit, is actually a good process, is actually a good model to fit to my underlying asset price. Before starting that, we saw certain preliminary, certain jargons. The first jargon was process, which is simply nothing but a collection of random variables. We very frequently use these words, but the technical definition of these is something that may not be clear. For example, the first preliminary that we did is process, which is nothing but a collection of random variables. For example, when I say my underlying asset price is a process, I know at every point in time my underlying asset prices can take multiple values. Hence, at each point in time, my underlying asset is a random variable. When I say ST, which is nothing but a collection of STs at different time periods, that is nothing but a process. Why? Because it is a collection of random variables. That's the first jargon. The second one is simply measure. Measure is nothing but the environment or a measure, a quantification of the chances of an outcome. We've looked at two measures in a binomial model chapter: risk neutral probability measure, real world probability measure. It's nothing but your entire framework under which probability measure, under which probability metric are you calculating. Are you doing everything under risk neutral probability measure, or are you doing everything under real world probability measure? For example, your risk neutral probability approach, probability into payoff into PV factor, where you're using Q is equal to e raised to r minus d upon u minus d, that is nothing but under risk neutral probability measure. The next jargon that we saw is filtration. Filtration is simply nothing but it's a metric, it's a measure that tells you what has been the history of the process and where are you currently standing in the process. For example, if I tell you F2, that basically means that you are standing at time 2. So it tells you two things: what has been the history of the process and where are you currently standing in the process. That is nothing but filtration. Claim, it's nothing but the amount received or the amount that I have to pay in or upon the maturity, upon the expiry of the contract, depending on whether I'm in a profit position or I'm in a loss position. The last preliminary was conditional expectation operator, which is simply nothing but it tells you, given the different values of the filtration, whether the expectation is a constant value, whether it's a random variable, whether it's a process. We took an example to understand it clearly. Let's say if I'm standing at time 0, 1, 2, 3, I'm calculating the expected payoff. I'm not calculating the constant payoff. I'm calculating the expected payoff, which is nothing but payoff into probability. If I tell you expected value of the payoff at time 3, given you're currently standing at time 0, I know this can take two values. I can either go from 0 to A or I can go from 0 to B. So I write the next level, which is expectation C3 given F0 comma A given F0 comma B. Now standing at A, you can again go at two ways: A comma C or A comma D. So I write this as 0 comma A comma C, 0 comma A comma D. Standing at B, you can go two paths: D or E. So 0 comma B comma D, 0 comma B comma E. And here I know once I'm standing at 121, the expected payoff is going to be a constant value, 33.1 into Q plus 8.9 into 1 minus Q. Hence I write that all these are constant values. This, because it takes two constant values, will be a random variable. This also will be a random variable because it's taking two constant values. And because this is taking two random variables, it's called as a process. This is nothing but what the conditional expectation operator was, given the different levels of filtration, whether it's a constant value, a random value, or a process. I'll take a pause. This is where we stopped last lecture. Any doubts, anyone? Didn't understand anything? All right, good to go, everyone.
So for conditional expectation operator, we need all the three things: random, variable, constant, and process.
So there wouldn't be any some kind of thing that we asked. I can probably give you a similar diagram, ask you to explain what a conditional expectation operator is. So you can exactly draw in the same way that we've written. Need not even write it in words. You can actually just highlight it as constant random variable the way we've done it. In terms of other questions that they can ask us, they can probably give you this. They can give you an expectation and ask you identify whether it's a random variable process or a constant value. These are the kind of questions, but I personally don't see anything coming from these set of preliminaries. It's broadly there for you to understand conceptually what we are going to study in the fall. This conditional expectation operator is never going to come in anywhere in the concept. For the sake of completeness, it's there, but it's just to conceptually understand broadly. If I would have been the setter, I wouldn't have asked because I have much better things to ask. All right. Any other questions? All right. Now let's do a bit of practical sense to understand. So what I have is, just give me a second, I'll put the image over there. So Wi-Fi issue. Just give me a minute. I'm just pasting the images there that I need to explain. Now it should be. Let me just take this. Sorry guys, it's just my network that's not working. Give me a second. Switch. Let me paste it. Finally. On. Fine. Sorry. So now let's start with this. So what I've done is I've just taken the graphs of Nifty and Standard Brownian motion. Now, what is the premise? What is the reason for considering Standard or Brownian motion in order to predict my underlying asset price? Now, for now, assume this is a graph of something called as Standard Brownian motion. we'll do formally what SBM is or what standard Brownian motion is. But the first graph, this graph is for Nifty, and this graph is actually of a standard Brownian motion, which is nothing but a Brownian motion process at the end of the day. Now, if you see, can you tell me what are the similarities that you observe between these two graphs first? Any similarities that you observe between these two graphs? Just by visually, what's the first thought that comes in?
Both are continuous.
All
They are
right, both
random.
are continuous, perfect. They are random. Can I say because of the
Their
randomness and
prices,
sorry,
fluctuations in the price.
perfect.
Fluctuations in the price.
All right, these are correct. So the first one is I know both of them work under continuous space, which is a good thing because my Brownian motion is something that I need to predict to my underlying asset price. Second, they are random movements. There is certain sharpness, there are certain spikes, there are certain fluctuations in both the processes. Hence, there became the premise that standard Brownian motion somewhere replicates, somewhere mirrors the behavior of the underlying asset price. The second important property is what I've done here is these are just zoomed in version. So this is the original graph. I've zoomed in this particular portion of the graph, which is this entire graph. And then I've again zoomed in this portion of the graph, which is this entire graph. What does this tell you is no matter how granular you go in, no matter how much you zoom in, the randomness still stays, the sharpness still stays, the random spike still stays. Let's see if this property holds true for standard Brownian motion as well. This is the original graph, zoomed in over here, which gives this graph. Zoomed in over here, which gives this graph. This is again a zoomed in version of this particular graph. Even here, whenever you zoom in, no matter how granular you go, the randomness still stays, the sharpness still stays, the behavior of the Brownian motion is actually still mirrored or reflected by the underlying asset price, which is Nifty in this particular example. Hence, as experts said that considering these properties and especially the granular time property still holds true, you can use standard Brownian motion in order to predict your underlying asset price or in order to model your underlying asset price. But there's a very big but. Can you all see any dissimilarities between these two graphs now? Let's see if there are dissimilarities.
Yeah. Negative.
Perfect. So the first point is SBM has gone negative, but I know my underlying asset price generally is not going to go negative. There may be very rare scenarios like crude oil during COVID, commodity crude oil physical, but apart from that, generally it's not going to go negative. So SBM can go negative, whereas underlying asset cannot go negative. Any other dissimilarity you'll see?
Very high fluctuations in the standard Brownian motion as
But
compared
if
to
you
underlying
see
assets.
this is from the range negative 0.221. It's just the graph axis for now. This is negative 0.221, whereas Nifty is actually 2000 to 12,000. So accordingly, this is from 2000 to 12,000, but this is in the range of negative 0.221. You are on correct lines, but your observations will now flip, or your dissimilarity will flip.
Means, Nifty is very high fluctuations in Nifty and
Exactly.
very low in Brownian motion.
Perfect. Can I say that underlying asset has higher volatility than SBM? Reason being, I know over here this particular axis or the standard Brownian motion is moving in the range negative 0.221, but my underlying asset price over the same time period has gone from 2000 to 12,000 in movement. Hence, here the volatility is relatively higher than standard Brownian motion. For the same axis, the extent of movement is higher. There are four dissimilarities. I'll tell you all that. Two of you all have correctly identified. Any others? Okay, chalo, I'll tell you starting point. That's one of the dissimilarity. Uh, this value starts from 2000, goes to 12,000.
Only standard Brownian motion is lies between means
Yeah,
0
0 to 1.
1 to -1.
Perfect. So this is starting with zero only the origin. So it's a property that SBM is always going to start from zero. We'll do it when we do it formally, but SBM has a zero starting point. Whereas I know my underlying asset, generally equities are going to go in the market through IPOs. I know whenever an IPO gets issued, none of the IPO starts with price zero. They're always going to start from a non-zero starting point. Hence, SBM has a zero starting point, whereas underlying asset is going to have a non-zero starting point. Now there's one more dissimilarity, which is for trend. I'll give that hint to you.
The Nifty is showing upward movement throughout.
Perfect. So SBM, if I see SBM, it is generally moving around a particular mean value or towards the origin value because it's for a smaller time period. So SBM has a flatter trend, whereas underlying asset has an increasing trend. In this particular example, we've taken increasing trend, but it can have a decreasing trend also in exceptional basis. For example, Vodafone Idea. We know it has crashed. Yes, Bank. We know it has crashed. So in the long term, that is having a decreasing trend. But I know generally in the stock markets, in a longer term period, my underlying assets are going to have an increasing trend. But we'll still account for both increasing trend and decreasing trend. Now, you all have correctly identified these dissimilarities. So, what people said is, all right, you are seeing certain inherent similarity between standard Brownian motion and underlying asset price. No matter how much granular you go, the nature still remains the same of both the graphs or both the properties. The randomness, spikeness, sharpness still stays. You can use your Brownian motion in order to model your underlying asset price, but you need to solve for all these four dissimilarities, and the revised Brownian motion that you get, you need to use that Brownian motion to predict your underlying asset price. Hence, what they said is this SBM that you are taking, it's fine to use it because you've proved us that there are certain similarities, but in this, you need to account for trend, you need to account for your volatility, you need to account for your starting point, and you need to account for your negativity. Once you solve all these four dissimilarities in the standard Brownian motion, you will get a revised Brownian motion. We'll actually do the technical names when we do this, but just for the purpose of now explaining, we'll get a revised Brownian motion. This revised Brownian motion is something that you can then use to model your underlying asset price. Now, the entire chapter journey is the same. We'll first formally understand what the defining properties of standard Brownian motion are, which process will be called to be a standard Brownian motion process. Post that, we'll go to the journey of solving each of the dissimilarities. We'll see how each of the dissimilarities are solved for, and we'll then arrive at the new Brownian motion, which will not be standard Brownian motion. If you all want to note it down, it's called as geometric Brownian motion. This is now what the next part of the chapter of Brownian motion is. If you all want to copy this, then I'll go to the dissimilarities up. Was it easier to understand with the help of these graphs?
Yes, sir.
Okay.
Sir, can you please scroll up? I want to write.
Hmm. Everyone done with this? Oh, let me go over here. This is your dissimilarities. I can dictate as well if my handwriting is very good over here. Similarities all noted down now. Take it. Let me. I don't know how I've written. Take. These are the similarities and each are the dissimilarities. And then here are your dissimilarities.
Done, sir.
Done? Let me know if others are done as well. Perfect. Thanks. Or let me know, Ashok, once you are done.
Dis- yes, sir. Dissimilarity is noted.
All right. Perfect. Now, let's first formally do. Now, for now, I told you I'll assume there's something called a standard Brownian motion. Let's formally do what standard Brownian motion is. Now, let's write with the definition. A process BT. Yeah, Anushka.
Sir, sir, we noted that standard Brownian motion will start from zero, but it can be go negative also.
Yeah. It is going to start from zero. So the starting point of the standard Brownian motion is going to be zero. From here, it can move anywhere. All right. Now, a process BT, I'm giving the notation of BT to a standard Brownian motion. For this, the notation can be anything. It's not a standard notation. I'm saying let this process be called as BT. So a process BT where obviously T can go from 0 to infinity. What this says is there's a process BT where the time period can go from 0 to infinity. A process BT is called as standard Brownian motion if first B0 is 0. So only those processes that start from 0 will be called as a standard Brownian motion if they have continuous sample paths. That means it's a continuous process. There are no breaks in between. And finally, independent and stationary increments. Now, copy this down, I'll explain. A process BT is called as standard Brownian motion if these three properties will do more properties, but if these three preliminary properties are satisfied, I can call the Brownian motion process as a standard Brownian motion process. The first is it has to start at time 0, it has to start at value 0, it has to have continuous sample paths, and the increments, I'll explain what increments are. Increments of the process has to be independent and stationary. All right, now let me explain. So first point is fine. It basically means that the process has to have a 0 starting point. That means whenever I'm looking at the process, the starting point of the process has to be 0. For a standard Brownian motion, it cannot be a non-zero value. The second property is it has to have continuous sample paths. It cannot be the case that here you have the value, then the process starts over here. Such kind of breaks, any discontinuity, those cannot be present in the case of my process. It has to be a continuous process. Now, what do I mean by independent and stationary increments? First, let's understand what do I mean by increments. So let's say if I have time 0 to t, I call the process as BT. This basically means whatever is the Brownian motion process at time t from 0 to time t. It's nothing but the process value for time t. What do I mean by increment is, let's say if I have one more time period in the intermediate, which is BS, or rather S. Can I say over here the process will be B0, which I know is going to be 0. At time 0, the process value is going to be 0. At this time, can I say the process value will be BT? At this time, can I say the process value will be BS? Increment is nothing but BT minus BS. That is what increment of the process is. You are looking at one chunk or one period of the process. That is nothing but what a increment is. Hence, if I let's say have to break BT, can I write this as BS plus BT minus BS? I have the entire process BT. I'm breaking it down into two parts. First, I'm adding BS, and then I'm adding the increment to BS, which is BT minus BS. That is nothing but what do I mean by increments. If I have, let's say, time 0, 1, 2, 3, B2 minus B1 is an increment of the process. B3 minus B2 is an increment of the process. It's nothing but a difference between two time periods. That is what I mean by increments. Let me know if anyone has any questions over here.
Increment is clear, but what is independent? How?
That I'll explain. Alright, I'll explain that as well, then you'll copy. Now, what do I mean by first independent? Let's break it down into two properties. What independent means is, let's take a very simple example. I have GDP of India. Let's say I have it from 2026 is going on now. Let's say I have it from 2016 to 2026. I have a data of 10-year India GDP rate. Now, let's say I take two increments or two slabs of this data. one data I take it, let's say from 2014 to 2018, and the other increment that I take is, sorry, I said 2016 now. So let's say one cut I take from 2022 to 2024, and the other cut is from 2019 to 2021. Assume COVID not there. I'm just taking a plain vanilla case. Let's say from the entire data, I remove two cuts or two slabs of data, which is from 2022 to 2024 and which is from 2019 to 2021. What increment mean is that both these data sets, both these cuts do not have any predictability power on each of them. What do I mean by that? When you go to predict 2022 to 2024 GDP hypothetically, or when you look at that data, that is not influenced or that is not dependent or that is not required to have 2019 to 2021 ka data. The past is not influencing the future value of the process. That is what I mean by independent. It's independent in itself. It has no relationship with its own past. It has no predictability power from its own past. That is what I mean by independent. What do I mean by stationary is when I take both these data sets, the mean of both the data sets and the variance of both the data sets is constant. That is what I mean by in stationarity. You all have SRM 3 or 4, one of them, which is entirely on time series. Their stationarity is an important property. So there you'll understand as well what is strict stationarity, what is weak stationarity. But in simple words, what stationarity mean is when you look at these two data sets, when you look at two slabs of data sets, the statistical properties over time of this data remains constant. What do I mean by statistical properties? The mean of both the data set, the variance of both the data set remains constant. And why do I generally have this property is, I'll get to a bit of practical sense. Whenever you're creating models, for example, I'm creating the model for, let's say for an export-based company or an import-based company, whatever it is, I'm predicting what the PNL or what the profit and loss of that particular company is going to look like. Can I say GDP will be one of the factors that I test for in order to predict the PNL of the company? Because it's an import-export based company, GDP of India is going to make an impact over there. Let's say I took GDP as a parameter to predict my model or to predict my PNL. Now, if the mean and variance is not constant of GDP over time, can I say that the time period that I take in order to predict my variable is going to be heavily variable? If I take the data from 2024 to 2026, I may get a different result relative to a scenario where I use data from 2010 to 2026. But if the mean and variance or the statistical properties of the variable are constant over time, can I say that this variability reduces significantly? I know practically none of the variable are going to be stationary, because practically I know over time something having constant means something having constant variance is actually next to impossible. Hence, you perform transformation of variables. You take first differences, you take percentage change, you take log, you take exponential, whatever. You do all these transformations in order to make your variable stationary. Understood what independent? From the purpose of our curriculum or for the purpose of our thing, you just need to know that increments are stationary and independent. But let me know if you all have any questions in terms of what now is stationarity and independence. All right, quick revision. Increment is nothing but I'm looking at the process as part of two time period difference. That is nothing but additional. What is the increment in the process? That is what the increment is. I am saying that two increments are going to be independent of each other. I don't need the first increment value in order to predict my second increment value. Third, stationarity is simply nothing but over time, the mean of the process, the variance of the process remains constant. They do not change. For standard Brownian motion, the increments of the process have to be independent and stationary.
So, over time,
Sir?
mean and variance both are constant.
Sorry.
Stationary meaning over time, both mean and variance both are constant.
Constant, yes. That is weak stationarity. You also have something called a streak stationarity, wherein you said apart from mean and variance, even the covariance is constant. That means the correlation of both the data sets is also constant. That is what strict stationarity is. For us, weak stationarity is what we look at. Yeah, Anushka.
Sir, just to first said, if you want मीन्स बोथ द प्रोसेस का जो 2022 से 24 का डेटा है और 29 से 21 का, सो दोनों का मीन और वेरिएंस स्टैटिस्टिकल प्रॉपर्टी सिमिलर होना चाहिए.
Yes.
तो स्टैटिस्टिकल प्रॉपर्टी सिमिलर होना चाहिए इफ दे आर डिफरेंट, slightly
Then
different,
हाँ.
and we have to make them same. So if so in which year we have to make the transformation, means कौन से year के इसमें transformation
You'll
लगाएंगे
have to do it
2020.
both. You'll have to do it in both because it's a like versus like comparison. You'll have to take a first difference, let's say in both the cases, or you need to take percentage changes in both the scenarios.
Okay. और जिसमें वो सबसे ज्यादा सिमिलर होंगे वो वाला हम एक्सेप्ट करेंगे ट्रांसफॉर्मेशन.
Exactly. When you do SRM3, SRM4, I don't know which SRM is there, but there you will look at, so there's generally an ADF graph, ACF plot, PSEF plot, wherein it tells you ki what difference pe you need to stop. Do you need to stop at the first difference, second difference, third difference? It tells, that graph tells you which difference pe you need to make it stop so that your data becomes stationary. You will study all these when you do that one particular SRM. It's entirely on time series only, making it stationary and everything. All right. Now, any doubts with any of the three? Process is said to be a SBM if it starts at value 0, it has a continuous sample path, and the increments of the process are independent and stationary. Cool. Anyone copying anything? Done?
Yeah, done. Sir.
Perfect. Now, let's look at
Sir,
one more thing.
we need to write.
Sorry, Via. You're copying.
Yeah.
Take it. Let's hope now the image that I want to copy gets copied. Fine.
Can you repeat the point for independent?
Independent is nothing but that the first set of increments do not have any relationship or predictability power for the second set of increments. Both of them are independent of each other. All right, perfect. Now, let's, this graph may be a bit this, so let's park this for now. First, what are the distributional properties of standard Brownian motion? Now, a lot of where research books actually do not explain it, they do not explain this in a good way as to where does now distribution come in. Till now, what we've been understanding, there's a process which will have certain properties and I'll predict my process. But where does a distribution now come in is what a lot of research papers don't explain it correctly. Even for me, I've actually worked on a practical project which includes everything related to such processes. That is where I've got my conceptual clarity. But let's first understand where does a distribution and why does a distribution come into picture. Let's say I have, or I'm standing at till time t. Let's say this is time s rather. Let's say I'm standing at time s. I know the process is starting at time 0. It's a standard Brownian motion process. till time s, I'll know what the value of the process is. Now, let's say the problem statement that comes in is, I want to predict the value of the process till time t. I'm standing at time s. From time 0 to time s, I'll know what the actual values of the process has been. I need to predict, let's say this is, hypothetically, let's say this is Reliance share price. I know what the price of Reliance will be till time s. I need to predict what will be the price of Reliance from time s to time t. That is what my problem statement is. Can I say one path can be this particular way, the other part can be it can go in this particular movement, the third way can be it can move in this particular fashion, the fourth way can be it can move very downwards, the next way can be it can go upwards as well. Can I say I can have multiple simulations over here that can go in from time s to time t? Reliance share price can take any particular path that it needs to go in. Each can be unique. Each can be a unique path. Can I say this actually gives me the way, or this actually gives me the path that this follows a normal distribution? Ignore it. It's going in negative. I'm not taking it there. But for the purpose of simplicity, can I say this actually mirrors the behavior of a normal distribution graph, wherein the mean of the graph is going to control where the trend is going to be? Because, for example, I have this distribution at this particular way. Can I say here the average is at this particular point? Hence, all the movements or all the possible simulations are going to end at this particular point. So the mean is going to control where the average of the simulations is going to be. And can I say the wideness or the extent of variation is what the variance of the distribution will control? If, let's say, I assume that the volatility is very high, the simulations can go as high as this volatility. Can I say this will have to have a higher variance normal distribution? Hence, two part. The mean of the process is going to control overall where the trend of the process is going to be, or where the simulation is going to end on an expected basis. And the extent of variation is what the variance of this distribution will cover. Now, for standard Brownian motion, the distribution is normal 0 comma t. This you will understand. This is coming from a property of stationarity. You all need not get into now. When you all do SRM, you will understand. But the value or this process distribution for a standard Brownian motion follows normal distribution with parameter 0 comma t. Hence, I now say that the variance of this distribution for SBM is t, and we did one property wherein we said SBM has a flatter trend. Why does it have a flatter trend? Because the mean of the distribution is actually 0. It does not have any non-zero mean. So the average is going to be a straight line. That is why you have that issue that your SBM has a flatter trend. Understood? Because the mean of the distribution is 0. If it would have been something positive, I know the distribution would have been upwards and the mean would have been over here. But because in the case of SBM, the mean of the distribution is 0, I know I'm going to have a flat trend, because the average is equivalent to what I'm currently standing at. Everyone understood till here? All right. And the increments of the process, BT minus BS, is going to follow normal distribution with parameters 0 comma t minus s. Because if it's like, let's say for a 3-year prediction, the variance has to be 3. That is why I have the same time period over there. So this is the property of the distribution of Brownian motion. This is the property of the increments of the Brownian motion process, SBM specifically. So this is for SBM. This is for increments of SBM. Everyone understood where does a distribution come in? Because a lot of times students have the confusion that my process is such, distribution is actually something of this sort, which is not correct. The distribution actually comes in this particular fashion. All right. And this I've just showed you a practical graph. This is what has been taken on Python. Do you all want to get to where did I make this graph? Do you want to get into that complexity? Okay, copy this down, then I'll give you all a very layman gist of where have I done this entire thing. Copy this down, then I'll tell you. Your project may be around this only. So even you always prepare such a graph.
So the variance should be the time period.
In the SBM, variance is actually the time period. And I know that is why the variance, the volatility of SBM is lower, because if I'm predicting it for a 2-year period, the variance is just 2, which I know is very low considering time period, as the variance is going to give me a very low volatility in SBM. That is what we have to solve for. So all the dissimilarities you can actually link over here. We know a 0 starting point was in the property. So that was one dissimilarity. Second was of a flatter trend. I know the mean is 0. It is bound to going to have a flat trend. So I know the flat trend became because of mean 0. Now volatility was lower of SBM. I know the variance is actually T, is just the time period. Hence the variance is bound to have, the volatility is bound to be lower in this particular case. And the last was of non-negativity. I know this is just a normal distribution. If my movement is very close to origin, which was happened in this case, let's say the end of the process would have been here, the distribution was bound to go in the negative stage, because there is no restrictive power, or there is nothing restricting in this distribution which prohibits or which avoids for it to go to negative. Hence, you can all tie all your dissimilarities to now the properties of SBM. I just put my chart here.
Sir, BT is equal to BS plus BT minus BS, correct?
That is what one of the things will be. Now, but that's not the increment. Increment is just BT minus BS.
Then a very mean of taking mean in taking expectations on both sides, so it will be 0, and variance on both sides, then it will be like it is, there is no covariance part, right?
That is why independent.
Yeah, independent. Yes. So variance of BT is equal to variance of BS plus increment, variance of BT minus BS, right? So it will be T plus T minus S. So it will be variance of BT is equal to variance of CS. We can say like that.
Variance of BT will be T in that particular case. Yeah. Because
Variance of
S
BT.
plus T minus S.
Yeah. Therefore, variance of BT is equal to variance of BS plus variance of BT minus S. So it is S plus T minus S. So it will be T.
T. Yeah.
Correct.
Cool. Everyone done with this? Just the distribution. Everyone clear with this part? Copy. Copying. All right. Now, till the time everyone's copying, the project where I did this was actually we were validating something called as a CVA model for a particular client. CVA is nothing but credit valuation adjustment. If you all don't understand, it's fine. But what CVA is, and today whatever we've understood is first chapter binomial model, second chapter we did the option pricing of in the case of binomial model. What was this option pricing? Just considering or what the fair valuation of the option is going to be based on my market factors. If ST moves, this is the price. If K is this particular way, this is the price. The price or the valuation of our option is purely because of market risk factors. That is nothing but what you report as exposure to the regulator. But the regulator comes in and says you that in India, it's not mandatory to calculate, by the way. In US, UK, Middle East domains, it's mandated by the regulator to have this CVA adjustment. What CVA tells you, all right, you tell me that because of your market factors, the valuation of your portfolio is, let's say, 400 million. But there is certain risk that upon the maturity, the counterparty is not going to pay you money, which is nothing but the credit risk aspect of the instrument or the credit risk aspect of the derivative trade. The regulator tells me, tell me how much you are going to lose on an expected basis if your counterparty defaults on your payment, or what is that adjustment value today that you will have to account in your books given that your counterparty is going to not pay you. It's something like ECL only, if you all have worked or heard about ECL. So what I tell my regulator is, all right, out of this 400 million, 20 million may be such an amount which I'm not going to get if my counterparty's default or the expected default amount that is there today. This is nothing but the credit valuation adjustment. I make an adjustment over and above my fair valuation to account for the risk that my counterparties are not going to pay me money today. Now, in order to predict this amount, in order to get this CV adjustment, I will have to value my option put. Let's say my 400 million is entirely option because we now understand options. Let's say this entire uh, adjustment, the amount that I need to calculate, I'll have to predict my underlying asset price for that in the future. Let's say my 400 million entirely is on Asian Paints. I'll have to predict what the Asian Paints share price is going to be for the next 3 years or whatever is the maturity of my option portfolio. In order to do this prediction, I'll have to fit a model to Asian Paints because I'm predicting ST on a frequent basis. This is nothing but the prediction of Asian Paints. Wherein, let's say I know the value of Asian Paints till 2017, I'm predicting the value from 2017 to let's say 2018. I can have multiple simulations. So what I do is I fit a Brownian motion to Asian Paints, and this is through a process called as Monte Carlo simulation. If you all have heard about Monte Carlo simulation. What Monte Carlo simulation does is you fit or you punch in the parameters of your Brownian motion process, you assign the probability distribution, which is normal in the case, in this particular case, and you tell him what number of simulations you need. Let's say I do 10,000 simulations. What it will do is, based on the distribution that you've given, it will give you 10,000 possible paths of Asian Paints between 2017 to 2018. So you got the price of Asian Paints throughout 2017 to 2018 in 10,000 ways. Now what you do is you price your entire option portfolio for each of these 10,000 simulations. So I'll essentially have, let's say if this has on a monthly basis. So there will be 12 months into 10,000 simulations. I'll price my options for each of the month for these 10,000 simulations. I'll get the pricing of options. I have the exposure of options now for each of the 10,000 simulation. I multiply this by the probability of my counterparty defaulting. That is how I arrive at my adjustment value. That this is what my exposure at default is. If the counterparty defaults, this is the exposure, and I'm multiplying this by the probability that my counterparty will default. In that project is where we use this particular. So it's basically used to predict your underlying risk factors. If you want to predict interest rates, you fit such a Monte Carlo simulation. If you want to predict equity prices, you fit such a Monte Carlo simulation. And the inputs that you do in the Monte Carlo simulation is of your Brownian motion. All right. I know two application based, but it's used today in the practical sense, especially in Middle East, Ashok. If you enter in the Middle East domain, these kind of adjustments are what is frequently used because their CBUAE mandates banks to have this in place.
Yeah.
All right. Sorry. Yeah. 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 Anushka.
Sir, my question is about that normal, our
Yeah.
Brownian, standard Brownian motion follows the normal 0, t. So my question is about 0. If we want to make the average value 0, means there are some values are positive and corresponding same values are negative, then it's become the 0.
Yes. So it's going to end up to the same
So-
value at S.
So it is in the discrete manner. If we have to in a continuous manner, then expectation of x is equals to x into that probability of
In
distribution.
that case,
So
expectation of BT is actually equal to BS. Expected value of the process at time T is going to be equal to where you ended. That is when your average of the distribution is going to be a flat line.
okay, then it's become 0.
Understood?
So the expectation of BT is equal to BS means both are random variables. BT and BS are variables. So
No, BS
expectation
will be
becomes
a constant because if you're standing at time S, you will know what the value of BS is. You will know what Asian Paint share price is if you're standing today in the market. So this is a random variable because this is in the future, but BS will be a constant value because you are standing at time B at time S. All right. So now let's just Ria.
I didn't understand this expectation of BT.
This we'll do it when we do martingale. But what this basically means is if I have this, I'm standing at time S. I'm predicting my Brownian motion till time t. Now, for my mean to be 0, can I say the expected value or the mean at time t is going to be of these sorts? For the mean to be 0. Now, if I want to calculate the expected value of the process at time t with a 0 mean, can I say this has to be equal to Bs? Only then I'm going to have a flat line. Because if this is not the case, let's say if expected value of Bt is greater than Bs, my distribution is going to look something of these sorts. Expected value of the process at time t is greater than the value of the process at time s. That means from here, the average is going to be of an increasing trend. This is what I mean. So if your Bt, expected value of Bt is equal to Bs, that means you have a flat line. You don't have any trend. Because you are saying the average value at time t is equal to where you are currently standing.
So, like whatever value Bs is taking, that would be the expectation.
Yes, in the case of standard Brownian motion. Because only then I'll have a flat trend. If I don't have that, let me see this. Yeah. In this case, when I have expected value of Bt or the process value at time t, if that is equal to where I'm currently standing, only then will you have a flat trend. Otherwise, you'll either have increasing trend or decreasing trend. That is what it means.
So, like how it is 0, like I cannot.
The
get.
mean is 0 because if I'm looking at the increment Bt minus Bs, your 0 is with respect to is with respect to S. If it's positive, that means it's going to be somewhere of these sorts. If it's negative, it means it's going to be something of this sorts. So it's with respect to where you are currently standing. Understood?
Yes.
So it does not mean it has to be 0 over here. Alright, it's with respect to, it's with reference point of S. If I have a non-zero, if I have a positive mean, it's going to end up somewhere over here. If it has a negative mean, it is going to end up somewhere over here. The averages. So your distribution over here is going to look something of these sorts with mean equal to this. The distribution over here will look something of these sorts with your mean over here. Understood? So it is with this reference point of S. Perfect. So now to summarize, if a question comes in the exam, define or explain standard Brownian motion, you will write what I just write. First are the defining properties, wherein I know B0 has to be 0. The second point is it has to have continuous sample paths. The second are the distributional property, wherein the first I know is Bt follows normal distribution 0, t and Bt minus Bs follows normal distribution 0, t minus s. The next set of properties are of the increments, wherein I know increments have to be independent and it has to be stationary. So these are the 6 points that you will mention. It's just a summary of what we've done. Let me know if you all have any questions with respect to what we did, what standard Brownian motion is, or where does the distribution come in, why 0, what will be the mean, what will the mean control, what will be the variance control. Let me know if you all have any issues.
BT is a process, right?
Sorry,
BT is a process, like
BT is the process.
it's a
Yes.
time series, like it can be time series, like.
Yeah.
So, how do we assess whether the starting point is 0? Like, how can we identify?
Where the starting point is 0. That is what the property is. You will never be asked to identify SBM. That is what the property is. That is what we will solve for.
increments are independent and stationary.
Sorry?
Independent increments are increments of BT are independent and stationary, right?
Yeah. Whoever is done, just put the title Solving Dissimilarities.
Stationarity means that statistical properties, mean and variance are same. Correct.
Yes.
So in practice, we use Brownian motion for option pricing or even for the equity predictions.
You can use it for equity, FX, underlying asset being IR. IR generally they use Hull-White. They don't go to your Brownian motion, but Hull-White is also a Brownian motion model. All your prediction models are actually Brownian motion models only. Some variation of Brownian motion models.
But in our syllabus, mainly focus will be on option pricing.
Yeah, so y'all don't have models for prediction. We'll get this to Black-Scholes model, which will be based on the geometric Brownian motion. And we have one chapter, the last chapter, that's term structure of interest rates, wherein we see the different models to predict interest rates. We won't be studying how do you predict your underlying risk factors. Cool. Everyone done copying? All right. Let's start with solving for dissimilarities. Let's do the first dissimilarity. SBM has lower volatility than underlying asset price. Now, till now, what all I know is BT follows normal distribution with 0, t, and BT minus BS follows normal 0, t minus S. Let me draw the graphs that I know. I'll have this. I'll have this. I'm standing currently at time S. I need to predict the process value till time T. This is the value of the process. Draw it through so that I have space. And from here, I have my.
So once again, sir, this SBM has a lower volatility than underlying price, right?
Yeah, SBM is used to fit the underlying risk
But
factors.
SBM is associated with the options.
Yeah. Assume it's a normal distribution. Cool. So now SBM, the first dissimilarity is SBM has lower volatility than the volatility of your underlying asset price. We know that SBM is BT. Remember, BT is not a standard notation. They can give you YT, XT, WT, anything. They'll define in the question which Brownian motion is a standard Brownian motion. Now, BT follows normal 0, t. BT minus BS, which is the increment, follows 0, t minus S. Can I say, or rather, in order to solve this dissimilarity, I know why is volatility lower, because it's just the time period that you are predicting for. It's going to be bound to be lower. There is no fine tuning parameter. There's no controlling parameter in order to increase or decrease my volatility value. What I do to solve this is, let's say I come to a revised process WT, wherein I multiply something called as a diffusion parameter, which is sigma square. What I say is, I am now introducing a diffusion parameter. Sigma square is called as your diffusion parameter. Wherein, can I say that for SBM, sigma is actually 1, because only then Wt will become 0 comma t. When when sigma is 1, the process is actually my standard Brownian motion, because only then the sigma square will go off and you'll have 0 comma t. So I bring in a revised parameter, which is the diffusion parameter, which is going to control my variation of the process. What do I mean by that? Can I say if sigma square is 1, I get my standard Brownian motion. If I make sigma square greater than 1, that means I'm increasing the variance, because if sigma square is, let's say, 20% or greater than 1, if it's 2, then the variance is actually going to get amplified. In that case, can I say the spread of this distribution is going to increase? The possibility of movements. First, the movement was expected or it was restricted to this particular distribution. But now, because I have widened, I have amplified my variance, I've amplified my cone. Can I say the movement can now go much significant spread? If I can bring my sigma square to be less than 1, sorry, this is actually greater than 1, it's not equal to 1. What I did in the purple cases, I amplified my spread, I amplified my variance by making sigma square greater than 1. If I make my sigma square to be less than 1, I'm reducing my spread, I'm reducing my variance of the distribution. Can I say, in that case, my graph is going to look something like this? And now the movement will be much more restricted to a very smaller set of variance, or much smaller set of this. So I introduced to solve or to control my variance, to control my spread, to control my wideness of the distribution. I introduced this. Now remember, is no longer SBM, because I'm now making changes to my standard Brownian motion. I introduced a diffusion parameter sigma square, which if equal to 1, I know is SBM, because the distribution I'll get is 0 comma t. If sigma square is greater than 1, you will have a higher volatility. If sigma square is less than 1, you will have lower volatility. Lower volatility relative to SBM. Everyone understood till here? This is the first issue I solved for. That now I have introduced a new parameter, which is sigma square, which is called as a diffusion parameter, through which I can now control my spread or the volatility of the Brownian motion process. If it's a higher volatility, my sigma square is generally going to be 1, which will now mirror or reflect the higher volatility of the underlying asset price. Everyone understood till here?
Sir, just one question. This SPM is associated with the options pricing only, you know?
No, it
Yeah.
can be with anything, any risk factors.
For understanding purpose, we are assuming that it is option pricing, right?
No, it can be anything. For this chapter and the next chapter, it's not necessary only for options. All right. Now
What is W here?
I've just given a notation to this Brownian motion process. There's no formal name till here. When we solve volatility, which we've already solved for, we'll solve for trend and we'll solve for starting point. Then we have a technical name to the Brownian motion. This is just like an intermediate step, because I'm not going to use a Brownian motion which accounts only for volatility and not trend. So we'll solve for trend plus volatility plus starting point. Then the process is called as general Brownian motion. That time the name comes in. This you can give any notation, YT, XT, ZT, whatever.
The same BT, since we are using sigma, we are using different.
Sorry.
The same BT follows normal distribution, but since we introduced the sigma square, so we are using different.
We are using WT, because I cannot use BT, because now it's no longer an SPM. Everyone understood this dissimilarity solution? Any question? Okay.
If sigma become 1, it reduces to Brownian motion, SBM, right?
Here is
See, it's a general form of a Brownian motion.
Let me know once you are done.
I mean, what do we call sigma here? It's a volatility or
Diffusion parameter.
diffusion.
Yeah, and it's estimated based on the, let's say if I have Asian paints, I'll take the historical volatility of Asian paints and that is what I'll use over here because I need to mirror that volatility.
Here we want to prove that SBM, maybe futures or anything, equity has a lower volatility than underlying price, right?
Sorry?
Here we wanted to prove that SPM has a lower volatility than underlying price, right?
We solved for it. That was the dissimilarity and we solved for that issue. We didn't prove that issue. I think
Yeah,
you joined that.
that is a statement we have to prove, right?
We did the similarities, dissimilarities before you joined, I think.
Yes.
Done, sir.
Anyone else copy?
Done.
Perfect. Let's go to the second dissimilarity then. I know the second dissimilarity was that SBM has a flat trend, whereas underlying asset has an increase in trend. We'll solve for both increasing, decreasing, but I know generally it's going to be an increasing trend. Now, I know till now all dissimilarities, remember guys, are additive. We've solved for the first dissimilarity. The second dissimilarity assumes that the first one is already solved. So I know WT follows normal distribution with, let me write it through a different pen. Okay. I know WT follows normal distribution with 0, sigma square T, and WT minus WS follows normal distribution with 0, sigma square T minus S. Now we will solve for drift in this particular process itself, not SBM. So now, if I draw the graph, let's say I'm currently standing at time S. I am predicting it till time T. Let's say this is what my process is looking like. Now, let's say this is my distribution. Let me make it a bit. So now, to solve for this particular issue, I bring in something called as a drift parameter, which is nothing but instead of 0, I bring in another mean parameter, which I call as mu, wherein mu is nothing but your drift parameter.
So that is X or mu. Mu follows
X or mu, meaning? sorry, I introduce mu into t, time dependent parameters. So this will become, just a second, mu t, normal distribution mu t minus s, comma sigma square t minus s. So what I do is, instead of a zero mean, I've added this t later up, whoever copied. I introduce a drift parameter which I make it time dependent. For example, if mu is, let's say, the long term average or the average value is, let's say, 2. I know if I take a 10-year prediction or if I take a 2-year prediction, the extent of trend is going to be different in both of the scenarios. The 2-year one may not have that much of an increasing trend, which a 10-year prediction is going to have. Hence, I also introduce a time parameter over here. So mu into t is what your mean is. Mu is called as your drift parameter. Now, what does this mean? I know this is my classic case of standard Brownian motion where I'm standing at time s, this is time t, and I know this is the mean of the process. This is the scenario where mu is equal to 0, where you don't have any of the drift parameter. Now let's say if I want to have an increasing trend, the distribution has to end at a higher level. The expected value of the process at time t has to be higher than the process value at time s. Can I say my distribution, therefore, in this case, has to be somewhat of these sorts, wherein this is now the mean? How can I shift the distribution entirely upwards? By making the mean positive. If you want to just change the spread, you control the variance. But if you want to change the location of your distribution, want to shift your entire distribution upwards or downwards, you can do it by controlling the mean parameter of your distribution. Hence, this is where relative to BS, there was no trend, there was no mean. But if you wanted an increasing mean, you make your drift parameter to be greater than 1 or greater than 0, sorry, not 1. If your mean is positive, you will shift the entire distribution upwards. Relative, if your mean is negative, if let's say you want a decreasing trend, you want your distribution to end somewhere over here, that is the expected value because that is what the trend is. You make your distribution, you shift your distribution downwards by making mu less than 0. So mu is equal to 0 is where your trend is flat. If you want an increasing trend, the average has to end upwards. You shift your distribution upwards by making mu greater than 0. If you want to shift your entire distribution downwards because there's a decreasing trend, you make your mu negative, which is what your drift parameter is. Everyone understood with this? All right. So xt minus, this is where I introduce my drift parameter for increment. For the process, it's time t. For the increment, it's going to become t minus s, which will be the time period. So I have mu t minus s. Oh, anything else? If mu is equal to 0, you will have an SBM, which is nothing but a flat trend. If mu is positive, that means greater than 0, you will have an increasing trend. If mu is negative, that means less than 0, you will have a decreasing trend.
Volatility has no role in playing trend. Volatility, that's sigma.
Volatility will have just in the variance, not in the trend.
No role in that.
No role, yeah.
For shifting the distribution, right?
Let me know if anyone has any issues in understanding, any doubts, or didn't understand anything.
No, I was just confused between mu because in normal distribution we use mu for mean, right?
So this is a parameter mu that has come in. First, the mean of the distribution was 0. Mu is not equivalent to mean. Mu is the parameter that I'm bringing in, which is going to control the trend. So the mean of normal is not mu in this case. The mean of xt is actually mu t. Okay, forget about the definition that mu is the mean parameter. Here, if the parameter of normal distribution, the mean parameter of the normal distribution is mu into t. Mu is that parameter which is going to shift your distribution. And t is nothing but will control if it's a 2-year prediction, the trend will be relatively lower. If it's a 10-year prediction, the trend will be relatively higher.
Sir, we introduced a diffusion parameter, right? Sigma. It has no role in playing the trend, right?
Yeah, that's what I said when you asked. Sigma square is going to control the variance, the location, the shift is just controlled by drift.
Two parameters, drift and diffusion, and drift for mu and diffusion for sigma square, correct?
All right. Ashok, clear with the confusion?
Yeah, yes, okay.
Let's solve one dissimilarity, then let's take a break. Fourth dissimilarity will solve post.
Sir, in this case, we also say that our random variable is changing. So according to that, our mean and variance also change.
Yeah, I mean, based on that, your mu and sigma square will take different values. If let's say you have Vodafone ID as a share, you know mu is going to be negative because it has crashed. But if it's going to be Nifty, you know your mu is going to be positive because it's going on an upward trend in the long term. So your mu and sigma square is going to take account of the specific nature of the underlying asset price that you're predicting. For different risk factors, you'll have different values of mu and sigma.
Sir, we start from BT, then omega T, then XT, right?
Then drift, yes.
Omega or W it is? Omega.
These are not standard. You can write any notations. I have written WT.
W.
Next dissimilarity we'll solve for is non-zero, a zero starting point. SBM has a zero starting point, whereas underlying asset will have a non-zero starting point. And then we'll take a break. The next one is because it's relatively easy. You all are liking FE till here?
I mean, too many concepts to remember. That's challenging. In FM, it was like formulas and we solve. So that was that. But
This
here,
has a new concept. That's good. ETOs will have more.
So one more thing, SBM, sir, we told it associated with the futures or equity or options. So we can say that option has a lower volatility than equity, right?
So Brownian motion is not specific to the derivative. It's specific to the underlying risk factors. You cannot associate Brownian motions with derivatives. It's going to be associated with risk factors.
So if you take equities and options, so then option has a lower volatility than equity, right?
Again, you cannot associate Brownian motion with options. You'll have to associate Brownian motion with the underlying risk factors of the option.
Okay.
You can have in that way equity options also. So in that case, the standard Brownian motion is fit only to equity. It's never fit to a derivative instrument. If it's futures, then if it's a commodity future, it'll be fit to your commodity. It's used to predict your underlying risk factor, not the option price. All right, that make it clear, guys. Your Brownian motions are always used to predict your underlying risk factors upon which you will price your derivative. All right, done copying. All right, let's do the third dissimilarity. SBM has a 0 starting point, whereas underlying asset has a non-zero starting point. Okay. Now, till here, what have I solved for is I know xt follows normal distribution with parameter mu t comma sigma square t, and xt minus xs follows normal distribution with parameter mu t minus s comma sigma square t minus s. In this, till here, we know that x0 is 0 because we haven't solved for it. Till here, x0 is 0. Can I say the graph is somewhat looking like this? You will have a prediction wherein the trend will be controlled by mean, the variance will be controlled by volatility. We've solved for this particular part. Now, what the issue they are saying is the starting point is not 0. The graph is going to start somewhere over here, let's say, because it's going to start from a non-zero starting point. Can I say the graph is actually going to look like this, but just at a higher variable or at a higher value? Because the pattern is what I've replicated. The trend, the direction of change, and the extent of change is something that I've already replicated and solved for. But what I need to solve is the entire curve or the entire distribution has to shift upwards, because it cannot start from a zero. It cannot start from a zero value. Can I say I can solve that by adding a non-zero constant value over here? So what I'm doing is I'm shifting the entire curve, entire graph by a non-zero constant or by a non-zero starting value. Now here remember that x0 is a non-zero starting point. It is the process value at time 0 which cannot be equal to 0, because previously it was 0. Now I have solved for it by adding it to the mean of the distribution. Where I'm now saying it's not going to start from 0, it is going to increase by the amount that it started with. Can someone tell me what will be the distribution for xt minus xs?
xt minus xs plus mu t comma sigma square t.
And
This will be sigma square t minus s.
and drift parameter will be same. Other will be x0 plus mu t.
Alright.
I mean,
Reason being, xt has this distribution. Xs is also going to have x0 plus mu s comma sigma square s, because the starting point is going to remain the same irrespective whether I am at time s or I am at time t. The starting point was the x0. Hence, for the same process, the value of x0 is going to be constant in both the time periods. When I look at the mean, x0 and x0 is going to cancel each other out because I'm taking a difference. It will be mu t minus mu s, which will be mu t minus s. Hence, remember, for increments, the starting point is not going to make a difference because you're taking the increment of the same process. Hence, your x0, x0, which are the same values in both the case, are going to cancel each other off. Understood? So, this process, wherein you solve for the volatility, you solve for the drift, you solve for the non-zero starting point, is called as general Brownian motion. Everyone understood? Let me know if there's any question, if something is unclear. if there's any confusion.
So we will use both the equations.
Yeah, if you are asked for the process, it will be the first distribution. If you are asked for the increment of the process, it will be the second one, depending on what is or what we are working with, the process or the increments. Okay. Everyone done? Okay. Let's take a break. 9:55, 10. 9:55.
Yeah. Okay.
All right. Let's join back at 9:55. I'll keep this open in case anyone's got copying it down as well. Let me know once you guys are back.
So just a general question. So what will be the exemption cutoff for CM2 and CS2 in general? Will it be 65 or it will be less than that?
65 is the safe haven. If you're above 65, you'll get it with obviously 99% probability. I don't think IFOA will go below 62, low chances, and below 60, though I don't think so. Because then it comes upon their quality of the quality that they need to uphold. So I don't think it will go below 61, 62, but it can still go till 60 is what I feel. Like bachelors have been 62 if I'm not wrong. During my time it was same around 63 I think. So I think somewhere around 61, 62 to 65. 60 to 65 basically. If you are between that you have a chance. Below 60 there's a low chance that you may get it. Above 65 so you're going to get it. Above 65 I don't think it's going to get it.
Why I'm asking, because in the exams directly who are attempting, they have a cutoff even 58, 55 and all they have cutoff. But that is different. This is different.
Yeah, I don't think it'll go below 60 to be very honest. Because there, IFO knows everything is like there, they have much more clarity of how the paper was, how it was checked and everything. Here it's still a third party institute that's been conducted. So I don't think so it's going to go below 60. Personally, I don't think so it's going to go below 60.
If we get 65, we are safe. Otherwise, we have to pray the God.
Yeah, like 65 is 39, 39. PTSA 39, FE2, FE 39. If you're 39, then 39 you can score it.
Yeah. I mean, if it is a single subject, definitely we can. But all the subjects are having heavy concepts. I mean, individually it is easy. Individually, I don't think it is very difficult. But all together, when we are studying, we will getting confused.
Probably. That can be because essentially you all are studying CM to 100% only.
Yeah.
I'll have FIP also, no?
CS2 CS2 SRM1 is there.
FE plus PTSA makes CM2 complete.
Yes.
I think there's one more where there'll be thoda more, but this makes CM2 complete.
80%.
80% and 20% you all have in FIP or something, right?
Yeah, SRM2 I think. SRM2.
Where you have runoff triangles and those parts. That is where runoff ruin theory and everything. That's in SRM. So that will be another 20. So SRM2 is what you all are studying next sem that you'll study. Okay, so 80%, but you'll get clarity on CM2 this semester only. So, yeah, ho jaye.
Yeah.
But yeah, consider 65 as a safe one.
We will aim that.
Oh, before this, I actually need to do this. Now, till this, what we've done is we had standard Brownian motion BT. We accounted for the diffusion parameter. Now, can I say sigma squared T was the variance? I am essentially remember multiplying sigma. Why am I writing it this way? Because variance of sigma BT, variance of AX is what? A square variance of X. So sigma will come out as sigma square and variance of BT is what? T. That is how you have sigma T in the distribution. But you are essentially multiplying sigma to the standard Brownian motion. So I had my standard Brownian motion. I multiplied the diffusion parameter. I added the drift parameter. I added the non-zero starting point. And I got the general Brownian motion. So this is what your journey or your equation of general Brownian motion is. I had my standard Brownian motion, multiplied the diffusion parameter, added the drift parameter into time, added the non-zero starting point. This is what my general Brownian motion is. And the way you derive distributions from equation is you always start with your SBM. The distribution of SBM is what? 0, comma. What's the
T.
distribution of t? Perfect.
Sigma
0, comma t. Now
Sigma
I
t.
multiplied sigma.
Yes.
Remember, everything that you multiply goes as a square in variance because of this property. Everything that you add gets added to the mean. So now I'm multiplying sigma first. It will get multiplied as sigma square in the variance. Now whatever you add gets added to the mean. So this becomes normal x0 plus mu t, comma sigma square t. This is what is matching with what you have over here. So this is how you derive distributions based on the equation. We started with standard Brownian motion, accounted for the first dissimilarity of volatility, accounted for the second dissimilarity of trend, accounted for the third dissimilarity of non-zero starting point, and derived the distribution based on that. Any questions still here? The other thing that you'll want to see is if I have this equation, can I write this equation as xt minus alright, xt minus x0 minus mu t upon sigma is equal to bt. Can I write it this way? I have xt, x0 LHS, mu t LHS, sigma division. So I will write this way. Can I say this is nothing but looking something like x minus mu upon sigma is equal to z? The way you standardize your normal random variables, this is nothing but your variable, this is nothing but your mu, it's nothing but your sigma. So SBM is simply nothing but a standardization of general Brownian motion. The other way of looking at it. Standard Brownian motion is the standardization of general Brownian motion. Because this was my general Brownian motion, I'm essentially looking to standardize it. Alright, copy this down. We'll go to the last dissimilarity. Let me know if any of you have any questions. Done?
Yeah.
Perfect. Let's do the last dissimilarity, which is the fourth one. SBM can go SBM can go negative, whereas underlying asset cannot go negative. Now, what all are the different ways that you know of removing negativity? What all are the approaches through which I can remove negative processes or a negative sign?
Add another negative sign. Not multiply.
Sorry.
If you multiply another negative sign.
All right, but then because of that, a positive will become negative. The process has both positive and negative. You want to remove or make this entirely positive. If I multiply with a factor, then all my positives will become negative.
Negative trend becomes negative, no?
But if I have positive, even they'll become negative. It has to be a consistent transformation across all the across the process.
The under
Yeah, sure.
If we square, then it will become
Perfect. So the first
If
way
we
you can square. Someone else was saying as well.
Anushka.
I am saying this square, and second is we have to put our standard Brownian motion into 0 to 1. Both the 0.
ठीक है. Forget about standard progression. Let's take a normal calculus area. Whatever you have negatives, how can you convert to positive? Like for example, one that Ashok mentioned is you can take a square. That means irrespective of what values I have, if I square all my value, my negative will become positive, positive will stay positive.
Second is mod. If we take the mod of the values.
Perfect.
we can add a very huge number, no?
You can have anything. Not
If you add a huge number, it becomes positive.
No, it still become negative. I can have negative 100 million also. Why not? Alright. The second, as you said, Anushka, is correct. I can take a modulus. If positive it is, it will stay positive. If they are negative, it will become positive. So it's ideally like this is x square. This is like your mod of x. Any other approaches? On similar lines that you can think of. If I make that transformation, everything that is negative will become positive and positive will stay positive.
Value.
Value?
Log. If
Log can still go negative. Log of less than 1 is going to be negative. Any approaches that you can think? I'll tell you this. Between these two, there's no correct answer. Yeah, Bhavan.
No, sir, I thought of linear transformation and derivatives. But
I think about linear transformation will also always, depending on the
yes,
parameter, can go negative.
yes.
It's something on lines of square, like it's a transformation only.
Expectation means that we take the derivative
take variance.
from the mean we take. Yeah, उसका नाम नहीं याद हो रहा.
Square root, huh?
Square root, but if it's a negative number, then not defined. It will become a complex number. The number value can change as well. I know in this, If I have -2, the answer will become 4. It's fine if it's such a transformation as well where the number changes. It's not like your -2 has to stay 2. It can, the value or the outcome can change as well. That's fine.
Take consecutive differences of.
But if I have one positive and the next one is a lower positive, it'll give you negative. Okay, I'll write it.
Multiply by a non-negative quantity. No.
Won't make a difference. Your negative will still stay negative if you are doing something.
E raised to exponential, right?
If
I
you
thought
take
it matters.
if you take an exponential even for a negative number, the answer is going to become positive because e raised to -2 is essentially 1 upon e square, which is going to be a positive number. If you have e raised to 2, it's still going to be e raised to 2, which is still a positive number. Hence, any number that you take over here is going to become positive at the end of the day if I take exponential. Now, which one do everyone understood by exponential first of all? Now, if I look at each of the approaches, which approach should I use to remove negativity? Let's first look at that. Now, first we look at two parameters: whether the transformation is mathematically easy to handle and do I know the distribution of the transformation. First, I know d by dx of x square. I know very well the properties. I know integration of x square also exists. So square is mathematically easy to handle. I know the mathematical properties that will come in. So it is good from that perspective. But do you know the distribution of x square? If x follows normal distribution, what will be the distribution of x square? We know it does not say normal.
Chi-square.
That will become your chi-square parameters. And I know chi-square, I don't have a lot of statistical distributions, and CDF, PDFs are also difficult to handle. Hence, here, your distribution actually goes for a toss. Everyone understood what I mean? Because if it stays in normal, log normal, I still know easily everything approximates to normal. If I have log normal, I can easily convert it to normal. So these kind of transformations are easy. But once it goes to chi-square, there are 3 parameters, more number of parameters that will come in, or rather 2 parameters. There is the shape of the distribution that comes in. Life becomes a bit more difficult. Let's see if there's a much easier transformation with us. Now, mod of x. Is mod of x easy to handle? Do you have d by dx of mod of x easily available?
Difficult.
Integration of mod of x is also difficult. That's correct. Hence, here, in the first place, this is mathematically difficult to handle. And remember, you have to make an entire model on this because Black-Scholes is essentially a model on the Brownian motion. So this also, it's failing on the first check itself. Let's see e of x. Is d by dx e of x easy to handle? I know the answer is e of x.
Yes.
Integration of e raised to x, I know the answer is e of x. Hence, it's very much easy to handle because it remains the same thing. If x follows normal distribution, what does e of x follow?
Log normal.
Log normal. I know log normal is still fine for me because it's going to behave like a normal distribution. The parameters are fairly straightforward over here. So here, it is mathematically easy. And the distribution is known as well. Thus, the approach that we follow or the transformation that we'll follow is exponential. The transformation is not very difficult now. What we know till now is I have my general Brownian motion, which follows distribution x0 plus mu t, comma sigma square t. And I have the increment of this process, which is xt minus xs, follows normal distribution with parameters mu t minus s, comma sigma square t minus s. This is what your general Brownian motion is. In order to solve for this dissimilarity, you simply do nothing. Let's say the Brownian motion I'll now denote as st. It is nothing but exponential of general Brownian motion, which is simply exponential of xt. Thus, the answer becomes st is nothing but exponential of x0 plus mu t, comma sigma square t. Sorry. X0 plus mu t plus sigma bt. Because I know xt was what? X0 plus mu t plus sigma bt. St is simply nothing but exponential of x0 plus mu t plus sigma bt. Can I say the distribution of st will be log normal with the same parameters x0 plus mu t comma sigma square t, because I'm just taking an exponential of a normal distribution which will become log normal distribution. This st is nothing but your final geometric Brownian motion. Everyone clear till here? This is nothing but that revised Brownian motion which can now, or which has all the solution which are solved for all the dissimilarities that were there between SBM with your underlying asset price. You started with your diffusion, you multiplied the volatility. Where did that go? Yeah. You started with the trend, you added mu t. You solved for your non-zero starting point, you added a non-zero constant x0. You had negativity issue, hence you took exponential over here. Thus, this becomes that revised Brownian motion, which now you are very comfortable in order to predict or in order to model your underlying asset price. Comfortable? Or copy this down. No one is going to ask you this square modulus exponential. That was just there that apart given all the transformations, why do we take exponential?
Sir, scroll up.
Everyone done? Sorry, I cannot see the faces now. Yeah. Let me know once I have. And if I have any questions.
So we are going to use the equation of ST.
ST or XT, either one of them, either general or geometric. Depending, I'll tell you why. Let's say the value of x0 is such high that the process is somewhere over here. It's way above zero. Let's say that's the underlying asset. Now, if the distribution or the volatility of this risk factor is not that great to push it negative, when will it go negative? When it is close to origin and the volatility is so high that from the origin it's pushing it down to the negative domain. If it's not that scenario, I can very well use the general Brownian motion to fit to my underlying asset price. Because if it's well in the positive region and the let's say it's at the 5,000 rupees range, if the volatility is not that great that from 5,000 the prediction is going to come to zero, there's no need for me to use a geometric Brownian motion. I can very well use a general Brownian motion. So I can either use GBM or a general Brownian motion, or I can use geometric Brownian motion, depending on the underlying risk factor. For example, now for JPY interest rates, let's not take JPY interest rates. Let's take the USD interest rates, which were around 3% a few years back, and currently it's as well 4%. But if it's, let's say, around 3%, I know if I go to predict and the volatility is higher, the general Brownian motion may push it to negative. Hence, in this scenario, I can use a geometric Brownian motion. In those scenarios where I know it's not going to go negative and it's moving closer to the positive value and I don't want it to go to negative, I'll use geometric Brownian motion. But if it's way in the positive region and volatility is not that high that it's going to push it to the negative region, then I can still go ahead with my general Brownian motion. So I'll either use general or I'll use geometric, depending on the context. Everyone done? All right, just put the title additional properties. We'll keep it light only now. Now, these are some of the just additional characteristics or additional properties of Brownian motion. The first property is Brownian motion as non-differentiable sample parts. What do I mean by that? For example, let's say if I'm calculating d by dx of x square, the answer is 2x. What does this mean? That a square graph, when I zoom in into a very small portion, that behaves like a linear graph. That is what differentiation is. You are looking at a very small time period at a very granular time period, because of which the nature approximates to a different kind of function. Your a square function at a very small time period is going to behave like a linear function. That is what differentiation is. But in the case of Brownian motion, we'll do it quantitatively in the next chapter as well. But we've already seen that in the case of Brownian motion, when I have or when I'm looking at a small time period, even this small time period has the characteristic of Brownian motion. Even in this, when I look at a very small time period, it will possess or it will remain its properties of a standard Brownian motion. Hence, can I say no matter how much I differentiate, how much I go to a granular time period, the function, the characteristics do not change. The Brownian motion characteristic still follows the same, still gets carried forward. Hence, can I say it has non-differentiable sample parts? This is what I mean by the first property. With me? I'll write the second property, then you'll copy both of them. Second property I can write. The second property of Brownian motion is that Brownian motion is a Markov process. Brownian motion is a Markov process. What do I mean by Markov process? I'll write the definition of the Markov process. Markov process is a process whose future value is independent of its past and is dependent only on the value. Alright, what do I mean by Markov process? Markov process simply states that the future of this process, the future prediction, has no dependency, does not depend, has no relevance with its history. The history is not going to influence the future, but it is dependent only currently where you are. It is going to depend where you are standing currently. A very what do I say? A very common example is the HHD model. Again, Markov, SRM2 or SRM3 is purely on Markov. Your entire subject is related to Markov. Let's take an example of the HHD model. HHD is nothing but health sick death model. What it means is the probability of you going to the death state, if you are currently standing at the sick state or you are currently standing in the healthy state, is going to influence the probability of you going to the death state in the future. It's independent of 2 years pehle where I was standing currently. All right, let me draw it. If I have the health state, I have the sick state, I have the death state. Let's say 2 years back, I was in the health state. I'm observing it on a quarterly basis. Let's say today, I'm standing at the sick state. The probability of me going to the death state in the next quarter has no relevance to the state where I was 2 years back. It's going to depend where I'm currently standing. If I'm in the health state, the probability will be lower than what if I'm currently in the sick state. This is nothing but a Markov process. The future value of the process is independent of the past, but is dependent only where you are currently standing. That is nothing but a Markov process. And I know Brownian motion is a Markov process because the increments are independent. The future is just dependent on where I am currently standing. Understood? Copy both these properties down. We'll stop for today. Or actually, there are two more properties. Let's just do those two properties, the small properties only, and then we'll stop for today. All right, here you will go with the second property. Okay, let's do the properties tomorrow. Yeah, let's also heavy.
We can apply Markov process to the securities as well, right? In the stock market, like
Yeah. Generally, what will happen there if you are going to predict, you generally take an average or the variance of the history. So there we say it's a random walk because it can move anywhere randomly. But telling it as a Markov will be a bit tricky because the parameters that you use to predict your future is actually predicted based on the average or variance of the history. So
yeah, but
somewhere you are using the history to predict the future.
the historical pricing is already factored in the current price, so it is independent.
That makes sense. Yes. So if you're doing risk neutral, it's a Markov process because you are matching currently to the market. Done?
Yeah.
Let's just do a third property, which is time inversion property. Alright. Now, what is the time inversion property? Let's say you want to make a prediction for 2 years. So I want to predict B2 or I want to know what the B2 is. As part of data, you don't have the 2 year data, but let's say you just have 6 months data. That means you have B 0.5 data. What the issue is, you want to predict the properties of BT, but you are given or you know only B 1 by T. Correct? Can I say first B 1 by T follows normal distribution with parameter 0, 1 by T? Because BT follows normal 0, T. If I multiply by T square, or sorry, if I multiply by T, can I say this will become 0, T square into 1 by T? Can I say this will become TB 1 by T follows normal distribution with 0, T? Thus, TB 1 by T will have the same statistical properties as BT. So even if you have 6 month data, you can calculate the 2B 0.5 to get the same statistical properties as B2. This is what the time inversion means. That if you are making it more granular, you can arrive at the same statistical property as normal distribution. Understood? On similar lines, you have something called as a scaling property, wherein that's also the same. Wherein you know you'll be given something like, oh, just give me a minute. Wherein it'll be, let's say, something like BT upon C and scaling my time period by a proportion of 1 by C. Can I say this will follow normal distribution with 0 comma T by C? I need to get rid of this C. Can I say I'll multiply by root C? This will be normal 0 comma C into T by C. CC will get cancelled. So root C B T by C will follow normal 0 comma T. So even if I may change the purpose is, no one is going to ask you this, but the purpose is if your time period changes, you can modify this Brownian motion in such a way that it follows your normal distribution 0 comma T and has the equivalent distribution as BT. That is what the time inversion and scaling property means. If it's time inversion, then TB1 by T and root C B T by C, where C is nothing but a constant value, will follow the same distribution as BT. That is what the time inversion and scaling property mean. You can play around with your time and still come back to your BT distribution. All right. Copy this down. We are done with the additional properties as well. Tomorrow, there's just one last concept remaining, which is the concept from which you can get sums. Till now, everything is broadly theory. You can be asked to define standard Brownian motion, in which you write that 3 columns, 6 points that we did. You can be asked, like, how did you solve for a parameter, which are low chances. No one is going to ask you, how did you arrive to geometric from SBM, but that can be some theory question that can come in, and additional properties as a theory question. The numerical part is what we'll do tomorrow, which is martingales. That's the part where numericals can't come in. It's a very easy concept. If you all have understood till now, there is a very standard approach of solving those kind of questions. So that is what we'll see tomorrow, and we'll solve questions related to Brownian motion. Let me know if any of you all have any questions. Are you all understanding whatever is going on till now? I know it's a lot, but is it clear at least piece by piece? Then once you all revise, you all will be able to thread everything together.
Yeah, fine, sir.
Started at 8, 3 lectures, unit 2, chapter 1, linear process, and people's lemma. We covered Nifty versus SBM, similarities.
Sir, could you scroll down?
Yeah. Let's zoom out a bit so that I can do this. Bhavani present, Hansraj absent, Rishitej absent, Ashok present, Kaustubh absent, Riya present, Arnil absent, Yash absent, Anushka present, Abdul Rahman present, Oath absent, Ansh absent, Abhar absent, Tom present, Ashish absent, Dikshit absent, Samuel absent, Anto present, Fatimatul present, and Manav is absent. So the people I've marked present are Anto, sorry, let me go from start. Bhavani, Ashok, Riya, Anushka, Abdul Rahman, Tom, Anto, Fatimatu. I think that's it. Yeah. Is this the general attendance now across all subjects as well?
Mostly yes, even less.
Ah,
I think we have more attendance for a fee.
okay. It'll actually, matlab, not like that. There may be work and all, but it'll actually become difficult to study it independently on your own self because all the concepts are new and all the concepts are actually heavy across subjects, not just for this. Like for example, utility function. I know you all would have already studied ARA, RRA, doing the tests of ARA, RRA. All of that threading it independently becomes quite difficult. Insurance and utility.
Yeah.
Now the
See, if we don't have recordings, then that's all.
yeah.
Impossible to understand.
Okay, let me know once all are done. I've marked your attendance already, so that's done. I'll switch off the recording.